All right, guys, so we were in the middle of section 2.2 last time, and like I said, we were looking at, one of those examples with the three overlapping circles, so kind of like one of these examples over here. So let's take a look at our example that we had, and this is what we had worked on last time. So we had basically just gotten to the point where we had filled in all the numbers for all the different regions of these three overlapping circles, and this was coming from example 16, where we were basically talking about, okay, Devin, I would say keep trying if you can, okay? So with example 16, we were looking at, as you can see, we are talking about, after leaving the polls, many people were asked how they voted. So concerning propositions A, B, and C, they gave us these numbers, how many people voted for one or the other, or, that kind of thing. So using all of this information is how we were able to come up with our, Venn diagram over here. So the only thing left to do for us was to actually go ahead and answer these questions for part A and part B. So just to show you, the information that we had collected last time from the Venn diagram, we can basically see only 90 people voted for proposition A, which means they did not vote yes on any of the others. 166 people voted yes on proposition B only, and 201 people voted yes on proposition C only. And then of course you can see with that 123 being in the overlapping region between A and B. So basically 123 people voted for proposition A and for proposition B. Same thing with 57 people voted yes on proposition A and proposition C, and 81 people voted on proposition A and proposition C. You can see right in the middle we have a 0. So that 0 basically told us that there was no one who voted yes on all three of these propositions. And then outside you have that number 72, and 72 tells us that those were the people who did not vote yes on any of those three propositions. So that's kind of what information we have over here. Now looking at part A, they are saying what percent of the voters in the exit poll voted no on proposition A. So what percentage of voters voted no on proposition A? So what do you think this answer is going to be? How many people voted no on proposition A? Okay, so looking at the Venn diagram, how do you think you can come up with that number? How many people voted no on proposition A? So how are you going to come up with that number? Okay, so let me see. Isabel, you're saying you take 201, 166, 57. Okay. Cooper, you're saying add A in the middle between A and B. Isabel, and then you added plus 72. Burgundy, you're saying add all together and then divide by all the ones that do not have anything to do with A. Would we turn the 90 into a percentage? 90 plus 123. Where are you getting the 90 from? Or you're talking about the people who only voted for Proposition A. Okay. So the question is, yeah, because it's asking the people who did not vote for A, who said no on A. So if you think about this, let's get rid of this guy for a minute here. So if you think about this, all of these 90 people, of course, voted yes on Prop A. The 123 people are also part of the people, voters who voted yes on Proposition A, and same thing with these 81 folks over here. So the question is, how many of them voted no on Proposition A, which means, and I think Isabel, you had that answer, which means you are leaving all three of those numbers out and you're taking all the remaining numbers, adding them together, and then dividing by your grand total. Now, what was our universal cardinal number? I guess we never did calculate that. So what is this universal number going to be for us to even, move ahead with this calculation? So can somebody tell me what our cardinal number for the universal set is? How many total voters did we talk to at the exit poll? Yeah, very nice, Maribel. It's going to be 790. So you take each of these numbers, which are in our overlapping circles, plus that 72, which is outside. Add all of these numbers, that's basically inside of our universal rectangle. And that's where we are going to come up with the 790 from. So very nice. So this number here is going to be 790. Alrighty, so basically you are taking the 166, the 57, 201, and 72 and adding all of them together to answer the question here. So that's going to be, let's see, 166 plus 57 plus the 201, and then on the outside we had the 72. And this is where you actually divided by that universal number we just came up with, the 790. And then Aaron, your question was, do we convert this to a percent? So yeah, since they are specifically asking us what percent of the voters voted no, you go ahead and add up your numerator, divide by that 790, and what do you think this will come out to be? Okay, so Burgundy, you've got 62.8%. Maribel, you're rounding it to 63%. Alrighty, so let's take a look at this. When we add all four of these numbers, okay, so that comes out to be 496 divided by 790. And of course, when you divide these two numbers, you will get a decimal answer. So remember, to convert your decimal into percentage, you basically just multiply the decimal answer by 100, or just move your decimal place 2 places to the right. So this should be approximately 62.8%. If you remember the other day, we had talked about rounding our answers to 1 decimal place. So we definitely don't want to round this to a whole number, which some of you had 63 as your answer. Leave it at 1 decimal place. So we definitely want to round it to 62.8. Okay, and your second question here, part B, was asking what percent of voters voted yes on more than one proposition. So what percentage of voters voted yes on more than one proposition? So how are you going to calculate this? So again, coming back to our Venn diagram, what are you going to do? What percentage of voters voted yes on more than one proposition. Okay, let's see. So all the ones that are more than one, then divide by 790. So what would those numbers be, guys? Okay, Maribel, you've got 123, 81, 57. Very nice. And Aaron, you've got the same numbers. Yeah, so you are only looking at the ones that are going to be in that overlapping region, right? Between the two circles. So that's going to be like you guys have over here, the 81, 123, and the 57 from here. All righty, very nice. And of course, you would still need to, since you are calculating the percentage, you will still need to divide by our universal cardinal number, which is the 790. So that's going to be 123 plus 81 plus 57, and then divide that by 790. So what does this answer come out to be? Okay, I've got 33% coming from you guys. I'm not sure what this guy is doing. Okay, so if you are, again, you know, they will ask you to round this to one decimal place. So since technically you don't have a number in your decimal area, you can leave that as a 0. So still keep the same rounding rule, but just put a 0 at the end so you can still have the, you know, the rounding place value that they're asking you to do. So 33.0% is what your answer is going to be, because I think they are going to be particular when it comes to your homework. You know, if they accept 33 and don't count it wrong, that's fine. But if they do count it wrong, just type it in as 33.0. So you can see, you know, once you have your Venn diagram completed and you have all the numbers in there, you know, obviously it makes it easier for us to then identify, you know, any of the questions that they may have and come up with these answers over here. So that was just the last part that we had to complete from this example over here. So did anybody have any questions on this before we move on? Okay. Let's come back to our handout over here. So the next thing that I wanted to talk about from section 2.2 was about De Morgan's laws. And you know, we had seen De Morgan's laws in the logic chapter also when we were talking about, you know, how the conjunction and disjunction between two logical expressions can work. So you had seen De Morgan's law at that same time, and we're bringing that same concept here with our set theory also. So they're basically talking about, you know, if you use this idea of the distributive property from algebra, where, you know, the idea is you take the number on the outside, which is a, and you distribute it inside the parentheses. So you multiply a times b plus multiply a times c. So the idea is, you know, if they are all going to be numbers, so a, b, c are all three of them real numbers. So the idea is you can actually start by adding b and c first, which is going to be inside the parentheses. And then whatever answer you get, you can end up multiplying that answer by a. Now you will get the same result if you first distribute the a value. So you can see if we go ahead and actually multiply a and b and a and c first, and then add, you know, whatever answer those two numbers give you, you will still get the same result because you're just using, you know, order of operations differently depending on, do you add b and c first and then multiply, or do you multiply first and then add B and C? So the idea is, would a similar property work, when we are talking about the complement of a set, or if we're talking about a union or intersection of a set? So that's kind of what this next example is talking about, to try and see, are we going to get the same equivalent sets for part A and part B? So we are defining our universal set with 5 elements, 1, 2, 3, 4, 5. Set A has 3 elements, 1, 2, 3. Set B also has 3 elements, and those are 2, 3, and 4. So part A here is talking about taking the union between sets A and B and then taking its complement, right? When we put that little prime symbol over there. And we want to know, is it going to be equal if we take the complement of set A and complement and set B and do a union between those? So we'll start on the left-hand side first. We need to find out what is the complement for the union of set A and B. So of course, that means you have to find the union of set A and B first. So you take sets A and B, and you can see union tells us take everything and put it together. If there's repetitions, you only write it once. So 2 and 3 is repeating. You go ahead and write those once, and this is what your A union B will end up looking like. Now, when we're talking about the complement, again, remember, complement means whatever is not in this set. So A union B has the elements 1, 2, 3, 4. If you look at the universal set, you had elements 1, 2, 3, 4, 5, right? So 1, 2, 3, and 4 are part of A union B. The only number which is not part of A union B is number 5. So you can see in the complement of A union B, it's only going to have number 5, because again, by definition, whatever is in the original set should not be in the complement of the set. So you always look at the universal set. Whatever elements we had in A union B, none of those will be in our complement set. So that only leaves number 5, which can go inside the complement. So that was us calculating what the left-hand side will look like for this statement over here. Now we want to see, are we going to get the same answer when we take the individual complement of each set and then try and do a union between them? So if set A has elements 1, 2, and 3, A complement will have elements 4 and 5. If set B has the elements 2, 3, and 4, then of course the complement for set B will have the elements 1 and 5. So now when we try to do union between these two sets, you can see that's going to be 4 and 5, 1 and 5. So of course, when we take a union between those elements, you combine all of them together and you get 1, 4, and 5. Now look at that. That is not the same thing as what we had from that left-hand side. You just had element 5. This guy over here has elements 1, 4, and 5. So of course, those two sets are not going to be equal to each other. So that relationship is not going to work. Now part B was taking the same left-hand side. So you still have A union B, and then you're doing a complement on that. But on the right-hand side, you will notice we are using intersection instead of the union symbol. So you've got A complement intersected with B complement. So now if you look at these sets for A complement and B complement, but we are now talking about doing an intersection instead of a union. Remember, intersection is that overlapping area. So only what is common between the two sets goes inside of the intersection. So of course, between both of these sets, you will see 5 is the only common factor. Now, number 5 is the same thing as what we got when we did our left-hand side calculation for A union B complement. So you can see this actually is going to be equal to each other, but not over here. So this is actually just by using these sets as an example, they're actually showing you how the De Morgan's laws work for set theory. So basically you can see that part A does not come out to be true, but part B does. And if you go back and look at the section in the logic chapter where we had talked about De Morgan's laws, you will see they are replacing the union and the intersection symbol with our and or symbol for conjunction and disjunction. So it's actually working in the same way, but instead of logic, we are using set theory here. So what they are basically talking about, and again, you can kind of read this paragraph over here, but basically what they are saying is, this law for De Morgan's that we just looked at, it works for this example. It works for these sets that we were given, with the numbers 1, 2, 3, 4, and 5, with sets A and B. But can we say that this will work generally for all sets, all sets that we try to use De Morgan's law? So that's actually what they're doing over here. In the next part is they're saying, okay, let's try and figure this out in general terms. So if you look at this, when we're overlapping these two circles, it's breaking up our universal set into 4 parts. You have part 1 over here, which is of course going to be all the elements that are neither in set A or set B. Region 2 that is created is of course all the elements that are in set A, but they are not in set B. Region 3, of course, is the overlapping, which means they are in both sets A and B. And then region 4, of course, would be elements in set B, but they are not in set A. So if we try to use the same De Morgan's law over here, let's try and figure out what would be A union B complement. So you can see they're talking about, if you look at A union B, A union B is going to be all 3 of these regions, which means all of those overlapping circles. Now, when we talk about the complement for A union B, if A union B is going to be, region 2, region 3, and region 4, which means if you try to look at its complement, those will be everything that's not in these regions. So that's of course going to be region 1, which is going to be this outside area. So that's your left-hand side, which is going to be region 1. Now you have to verify that the right-hand side is also going to give you the same region, and that's how we know it's going to work for every set. So if you talk about A complement, now A complement is going to be everything that's not in set A. So, regions 2 and 3 are part of set A, which means region 1 and 4 are not going to be part of set A complement. For B complement, of course, anything that is not in set B. So set B is a combination of 3 and 4, which means the complement for B will be regions 1 and 2. Now remember, we are trying to verify that the intersection between these two sets will work. So if you take the complement of set A, intersect it with the complement of set B, you will see the only common region between these two is going to be region 1 over here. So again, you can see both of these are pointing to the same region, region 1, which is going to be outside of our 2 overlapping circles. So this was just a way for us to show that De Morgan's law is actually going to work for all sets A and B. It's not specific to a particular example. So in set theory, you can actually use De Morgan's laws for any sets when you are talking about these, intersecting and union of sets and their complements. So basically they are saying this one law that we just looked at is the complement of a union is the intersection of the complements, because you can see you are taking the complement of the entire union of A and B, and that is equal to the intersection for each complement of the set. So that's what they're talking about in that statement over here. So just a little paragraph here on Augustus De Morgan, who came up with these rules, and it's kind of neat. They're also talking about how he was the one who suggested using the slanted line for a fraction, which is something we are still using today. So just a little bit information on that. Now, you do have two different De Morgan's laws, and again, you saw those in chapter 1. So here is the one rule that we just talked about. Now, they are telling you in exercise 33, they are having you prove that the second law would also work. But again, you can see when you have a union, we use an intersection. When you have an intersection, we use a union to represent this. So the second law is the complement of an intersection is the union of the complement. So you will definitely, be helpful to remember these two laws in here. Now, you may not think about set theory being used in everyday examples in the real world, but we actually do a lot of set theory calculations. We may not always use Venn diagrams for those, but it's definitely something that we use often in our real world examples. So here's an example with the different blood types we have. So you've got type A, type B, of course, type A, B, and type O. So basically the idea is, depending on which molecules our blood has or does not have, that's kind of how they define what type of blood type we have. And again, they're getting a little bit into detail about, the scientists who basically observed the presence or the absence of two distinct chemical modules that basically, the red blood cells have. So he labeled one of them as A and the other one as B. So basically, whoever contains the A molecule is labeled as having type A blood. The people who will have B molecule in their blood type will be labeled B. Now, if somebody contains both of these molecules, A and B, of course, that's when they are labeled as having blood type AB. And if neither of those molecules is present, so that means they are absent, that's when you have blood type O. And whenever it comes to blood transfusion, if you need to receive blood or anybody else does, it really helps to know what type of blood type you have. So if that is something you are not aware of for yourself, you should definitely find out. I know I am O positive, which makes us universal donors, because since we have the absence of molecule A and B, mixing blood type O with any of the other blood types does not cause any problems, because if you mix the two wrong blood types, the blood can clump and cause a lot of trouble. So obviously anytime you're going in for surgery or anything like that, they are going to try and verify what type of blood type you have. So you can kind of see how we are again using the Venn diagram to show how we can again use set theory with these blood type examples. So you can see the two circles are representing the two blood types, A and B. Those who have the both type of blood are going to be in that overlapping region. And then folks who have blood type O, where they don't have molecules A and B, of course, they are going to be outside of those overlapping circles. It's really kind of neat how they are, kind of using set theory to define this. And you can see they are defining blood type A as, having the type A molecule, but not type B. So that's the B complement. Type B is where they have type B molecule, but not type A. So that's A complement. Of course, like I said, type AB is going to be the intersection between the two. And type O is going to be where both those molecules are absent. So complement of type A intersected with complement of type B. So we will come back to the blood sample example here in example 5, but very quickly, again, just to see how we can use these De Morgan's laws. So you can see again, we're defining set universal as going from the digit 0, 1, 2, 3, all the way to digit 9. Set A is defined as 2, 3, 7, 8. Set B is 0, 4, 5, 7, 8, 9. And they are asking us to use De Morgan's laws to find A complement union B, and then again the complement on the whole thing. So since you can see we have A union B in the middle and complement on the outside, even though you have A complement, you can still use De Morgan's laws over here. So basically you take the first set, which is A complement, and you take a complement on that. Union will become intersection on the right hand side, and then of course we take B complement. So think about this. The complement of A complement is kind of like having two negatives, and two negatives become positive, which means you're actually looking at set A itself. So you can rewrite this as A intersected with B complement. Set A is given to us as 2, 3, 7, 8. You are talking about B complement, which means everything in set B is not going to be in that B complement. So that's why set B complement has 1, 2, 3, and 6, which was not in set B. And then when you're talking about intersection, the only thing common between these two sets is 2 and 3. So you're not proving anything here. Now we are using De Morgan's law to help us simplify some of these examples over here. So let's take a look at an example where we can try and use the De Morgan's law for ourselves also. How about number 24 over here? So again, very simple, nothing too complicated. So number 24, and you can see we are defining our universal set again, going from digit 0 to 9. Set A is defined as 0, 2, 4, 5, 9. Set B is defined as 1, 2, 7, 8, 9. So De Morgan's law, you can see this one is A complement intersected with B, and then you're taking a complement on the whole thing. So since this is coming from the intersection, basically that's this law over here, the second one. So you can see when you have A intersect B and a complement on the outside, that means you take the complement of each individual set, and intersection will become union. So if we try and apply that over here, you would basically write this guy as we take the first set, take its complement, intersection will become union, and then you take a complement of the second set. So since you have a complement and then a complement again, you can basically rewrite that first one as just set A and union B complement. So what do you think this set will actually come out looking like? So don't send your answers just yet. Hold on to your answer. Just, if you want to type it and have it ready, that's fine. Don't send it. I want to give everybody a chance to come up with their answer. So when I ask you to, send it only then. Cooper, make sure you are participating with the class, okay? And I know some of you said you were having trouble getting your cameras turned on because your internet's not working. So again, for you guys also, please make sure you are participating, even though you're not, I'm not able to look at you. All right, guys, go ahead, send your answers in. We've got 6, 7, 8. So you are taking A union B complement once you simplify by using De Morgan's law. So what are the rest of you coming up with? Isabel, you've got 2 and 9. Cooper, 2 and 9. Rebecca, 2 and 9. Lisbeth, Macy, Logan, Ethan. Okay, so Aaron, what happened with your answer there? Okay, let's take a look here. So we are taking A. So that was a set with 2, 0, 2, 4, 5, and 9. And we are doing a union with B complement. So B complement is going to be everything that is not in set B. So let's see, we can have 0, 1, 2, we can have 3, 4, 5, 6, and then I cannot have 7, 8, or 9. So you've got 0, 3, 4, 5, and 6. And we are talking about union over here. Union means take everything and put it together. I think what you guys have done is, well, it's not even intersection because 2 and 9 is not part of B complement. So you would take 0 because we have 0 in both our sets. We would take 2 because it's in the first set. You would take 3 from the second set. Both of them have 4 and 5. So we would go ahead and write down 4 and 5. And then I have 6 from my second set. And I have 9 from my first set. So your union between A union B complement should be 0, 2, 3, 4, 5, 6, and 9. So what happened over here, guys? Because nobody had that answer. So either you were looking at each other's answers before you came up with it, or somewhere along the way your calculation did not work out, because Aaron, you also had 6, 7, 8 as your answer in there, and you can see, obviously that would be incorrect, and then some of you only had 2 and 9. So what happened here? Yeah, Cooper, you are not using set B. You are using the set B complement. So that's why whatever is in set B is not going to be in set B complement. That's the entire idea behind this exercise, because you have to see, how those De Morgan's laws would translate, and how you would come to the conclusion. So whatever is not in set B is going to be in B complement. And then you are taking the union between set A and B complement. So that's where the 3 is coming from. Okay. So you basically use set A and set B is what you're saying, Cooper? Yeah, okay. All right, I guess you guys are going to try number 26 all on your own. Let me see if you can do better this time. So number 26. Okay, so Markley, basically the way the De Morgan's laws work out is you take whatever your original sets are. So your original set is set A and B complement. So you take the complement on whatever those original sets are. So that's A and B complement. And then you replace your union with the intersection symbol. So, you know, when we were talking in terms of logic, that would be where you are taking basically the negation of each individual statement. So in this case, instead of negation, that's going to be a complement. So since your original set is A, when we do the right-hand side, you will have A complement. And then our second set is B complement. So that means you're doing B complement complement. So you're going to be taking a complement on the original, which is B complement again, and then replacing your union with intersection. Okay. That's correct, Ethan. Yeah. So what's not in the set will be in the complement of a set.
How do you do double complements then?
So double complement, kind of like how we did over here. So when you have a complement of a complement, that means you're actually looking at the original set itself. Okay. All right, guys, I'll give you about another 30 seconds or so to get your answer ready to send through. Not just yet when I ask you to. All right, go ahead, send your answers in. Okay. 178, 1, 2, 3, 4. Oops, that answer disappeared. Hold on. 1, 2, 3, 4, 6, 7, 8, 9, 0, 1, 2, 7, 8, 9. 1, 2, 3, 7, 8, 9, 1, 2, 3, 6, 7, 8, 9, 0, 1, 4, 5, 7, 8. Okay, 1, 7, 8. 1, 2, 3, 6, 7, 8, 9. 1, 2, 3, 7, 8, 9. 0, 2, 3, 4, 5, 9. Not again much of a consensus, though I think some of you did get 1, 2, 3, 7, 8, 9. I think a couple of you had 1, 7, 8 in there. Okay, so let's take a look here. Let's get rid of this right here. Okay, so for number 26, you are given, I'm going to try and do this here. So you have A union, B complement, and then of course we have a complement on that whole thing. So this is kind of what I was trying to explain with Markley. So you're taking A as your original set, but then you take its complement. You've got B complement, which is the original set given to us. So again, we take a complement on top of that. union will become intersection. So if we clean this up, A complement will stay as it is. We've got intersection, but since we have B complement of a complement, that will become your original set B. So that means we are taking the intersection between A complement and set B. So A complement would of course be everything that's not in set A. So since you have 0, this guy will be 1, 2 cannot be in there, 3, 4, 5 cannot be in there. So you can have 6, 7, and 8. So whatever is not in set A is going to be in set A complement. Okay, Markley, so you've got 1, 3, 6, 7, 8 in your answer already. So yeah, that's going to be our A complement set over here. Okay, got it. So now we are doing intersection with the B set, and B is given to us. So B has 1, 2, 7, 8, and 9. Now remember, this is intersection, which means intersection can have only what is common between both your sets. Of course, you can see 1 is common between both our sets. This guy has 3, that one has 2, so that's not going to work. 6 is not going to work. But then we have 7 in both our sets, so 7 will work. And then 8 is in both our sets, so 8 will work. So yeah, looks like Burgundy, you were one of them with the answer 178, and Logan, you also had 178. So looks like, again, did you guys end up doing union instead of intersection? Because I am seeing a lot of those repeating answers. Like Becca, you've got, all of the elements between sets A complement and B. Cooper, I'm not sure how you have a 0 in there. And then let me see, Maribel, you also had 1, 2, 3, 7, 8, 9. Aaron, you also had extra numbers in there. Isabel, Elizabeth. Okay, so it looks like many of you ended up doing, I don't know if it's a combination of union or what, but as you can see, you definitely had a lot more extra answers in there. Yes, Markley, basically that's a good guidance to go with. So when it looks like a U, it's going to be union. When it's upside down, kind of think of it as looking like an N. It's an intersection. So yeah, Maribel, you said you were doing a union. Elizabeth, you said you were doing a union also. So yeah, be extra careful, guys, because as you can see, it really does change your answer quite a bit drastically, because union and intersection are such different things that it's kind of going to mess you up. So again, use your homework for practice. You can always come up to your textbook pages, the ebook from your WebAssign account, and just pull up these exercises at the end of your chapter and try and use them for extra practice. Because the more practice you can get from this, the easier this concept is going to become for you. Okay, did anybody have any other questions before we move on? Okay, if you think of anything, let me know. So I did want to look at that example 5 over here, where they're talking about the blood type right over here. So they're talking about the American Red Cross has compiled a massive database of the occurrence of blood types in the US. Their data indicate that on an average, out of every 100 people in the United States, 44 have the A molecule, 15 have B, 45 have neither A nor B. So they want to know what percentage of the US population will have the following blood types. So they want to know for type O. So basically, again, you can see we are defining A for, Americans who will have the type A molecule. We are defining B as, again, Americans who would have the type B molecule. So as you can see, they are saying out of every 100 people, that means we are taking our universal set cardinal number to be 100. For type A blood, we are saying there's going to be 44 people in that set. For type B, again, they're telling us it's 15. And then they said 45 of these 100 people neither have type A nor the type B molecule. So you can see that is how we are defining it as the intersection. Aaron, yeah, you can use a Venn diagram, and I think they do have one over here. So, you know, when they are basically talking about these 45 people who have neither type A nor type B molecule in their blood, basically those would be the group we would define as people with type O, right? Because type O is the blood type where they don't have the A or the B molecule. So basically you can say it's the type O blood that is 45 out of 100. So basically to find out what percentage of people have the type O blood, that's basically going to be 45 out of 100, or basically 45% of basically the American population, we can say, you know, has type O blood. Then they want to know what percentage of people have the type AB blood. Now remember, AB means they should have both type A and type B molecule in that. So that's where, again, we kind of use this De Morgan's law, as you can see, and they're talking about using the complement rule. So you are looking at how many people have the type A and B blood, so that's your union. And then you are also adding all the people who do not fall into that union of A and B blood types, because you're looking at that complement over there. And then, you know, of course, we've got our universal set number over here. So basically, we know, and this is coming from De Morgan's law over here. They're using De Morgan's law, and we know that there are 45 people who do not have type A or type B blood. So that's going to be subtracting that 45 from our total of 100, which tells us A union B is going to be 55. But again, A union B of 55 has people who have only type A blood. It also has people who have only type B blood. We are specifically interested only in these group of people over here that have both type A and type B. So obviously that means we got to remove these people and these people out of these total of 55. So you will notice we have 44 people with the type A blood, 15 for the type B blood. So you guys take that. And then from that, we would have to subtract this intersection. And once you go through this calculation, you know, 45 plus 15, and then subtract that from 55, you basically end up getting 4 people. So out of these 100 people that we are talking about, only 4 of them are going to have the type AB blood type. So of course, you know, 4 out of 100 gives you only 4%. So that's going to be 4 people who fall in that overlapping area. Now, since you have 4 people in that overlapping area, remember those are the ones being counted in your A molecule and B molecule also. So when you try to answer these part C and D questions for, you know, what percentage of people have only type A or only type B, you will need to subtract that number 4 from this total. So you would have total of 44, from which you subtract 4. So that should be only 40 people. 40 out of 100 will of course tell you 40% of people have only the type A blood type. Out of the 15 people who have type B, again, we subtract these 4 that were type A and B. So that's going to give us just 11 people. 11 out of 100 would be 11%. And you can see once we do all of those calculations, you are able to, you know, also complete your Venn diagram. And just as a percentage, you can kind of see what this table ends up looking like. So you can see just by this little example, this little experiment, 45% of the people have type O blood type, which is the most common blood type. 40% for type A, so that's the next category of people or the blood type that we will see most common. Type B gets a little bit on the rarer side, but look at type AB. That's only 4%. And it is very hard, you know, when you are trying to look for type AB blood type, it gets very, very rare because only 4% of the population we are saying is going to have, you know, that given blood type. And then once we start introducing the Rh factor, you can see we can break this down into type O with positive and negative with type B, type A, and of course type AB. And look at that, AB negative. If you have 4 out of 100 people that have type AB, 3 of them are going to be AB positive and only 1 of them is going to be AB negative. This is the most rarest blood type you can have. And so it's kind of really neat. And your textbook has a little bit more on the Rh factor that I have not included in here. But you know, you're definitely welcome to go take a look at that distinction if you like. But just something to kind of see again how set theory is coming into play with these examples over here. Let me see if I had an example for us here. Okay, so towards the end over here, let's take a look at. Okay, so they are saying using the data in figure 2.34, you know, complete these questions over here, round off your answer to the 10th of a percent. So let's take a look at number 36 over here. And you know, when they're talking about figure 2.34, it's that table that I just got done showing you, this one over here. Oh, did I lose that? Okay, so this one right here. Okay, so we are looking at number 36, and number 36 is talking about of all the people in the United States who have type O blood, what percentage are Rh positive and what percentage are Rh negative? So let's do this. So what would you say? They're talking about type O. What percentage of the people are O positive and what percentage are O negative? What would you say? So from the people who are type O blood, out of those people, how many would be, you know, O positive and how many would be O negative? So how do you think you would calculate that value? Okay, let's see. Burgundy, you said 84.4 and 15.6. Aaron, you're saying for the total amount of people with type O blood add. Yeah, very nice. Exactly. So when you add 38 with 7, you know, of course, it's going to come out to be that 45 that we had seen earlier in this calculation. So we know there are 45 people out of the 100 that have type O. And then the idea is, you know, out of those 45 people, how many of them are type O and type, positive and negative? And you can see that's 38 and 7. So Burgundy, do you want to tell me how you came up with those percentage values? Very nice. Yeah, exactly. So when you are doing these calculations, you have to see how many people you had total who had type O. And then, of course, we know there were a total of 45 people who had, type O blood type. And out of that, they are telling us 38 are O positive. So that will be a fraction of 38 out of 45. And we had 7 people with the type negative, O negative. So that would be 7 out of 45. So when you convert these into percents, yeah, very nice. This would round up to 1 decimal place as 84.4%. And then what did you have for the other one? 15.6. And then you had 15.6%. And if you add these two numbers together, they will add up to 100% because, obviously they are going to be all the people who have the type O blood type. Alrighty, very nice, Burgundy. So that was the good answer. And that's exactly how you have to do. And you can see they're doing this for all the other blood types also. So you can definitely come up with your answer based on that. Okay. So let's clear this guy out. And now, these last questions, if you look at them, are actually very interesting because they're talking about, if a person has this type of blood, what types of blood may they be able to receive in a transfusion? So, if they had type A, well, what could be an acceptable donor? Type B, type AB, or type O. So if you look at the answer for number 41, of course, if a person has type B blood, obviously type B is the one that would be preferable. But remember what I was telling you with type O folks also? Since they do not contain type A or B molecule in their blood, that makes them universal donors because they don't have anything in their blood which will interact and cause problems for the type B blood type. If you look at type O, now that makes them very restricted because since they don't have the molecule A or B in their blood type, they can only receive blood type O for a transfusion. So what do you think for number 42? What do you think your guess would be? What kind of blood type can they receive if they have type AB blood? Who can be a donor for type AB? So if you have blood type AB, what type of blood can this person receive as in transfusion? Okay, so let's see. Then you've got A, B, and O. Burgundy, you've got A, comma, B, comma, O. O, A, B from Aaron, A, B, O. Okay. A, B from Lorena. Okay, O, A, B, Lisbeth. Logan, same thing. Rebecca, same thing. Yeah, so these guys, and I think there's a term for it that is not, so are they universal receivers or something like that? Is the terminology, because these people are actually able to receive blood from all 4 blood types. So they can actually have, like you guys said in your answers, yes, they can have type A, they can have type B, of course they can have their own type, which is AB, but they can also have type O. So these guys, like I said, are sort of like universal receivers because they can receive blood transfusion from any of the 4 different blood types, which is kind of nice because, obviously for people like them, you would be able to find somebody who would be a match in that case. All righty. Good job, guys. So that was our section 2.2. Now, the next section we are getting into is section 2.3, where we're actually getting into our calculations for counting. Basically, to figure out how many different options or, variations there can be. So if you just look at this initial couple examples that I have in here, we're talking about, if you went on a shopping spree and let's say you bought 2 pairs of jeans, 3 shirts, 2 pairs of shoes. They want to know how many, new outfits could we create from these different combinations. So, we're talking about 2 pairs of jeans, 3 shirts, and 2 pairs of shoes. So if you mixed and matched all of these different clothing items, how many new outfits could we create from them? In the second example, we're talking about, a compact disc, which is your CDs. Buyers Club sends you a brochure saying that you can pick any 5 CDs from a group of 50, today's hottest sounds. And they're saying, okay, we'll charge you, 19.95 for those 5 CDs. So again, if you have a choice of 50 different CDs to choose from and you have to pick 5 of them, well, how many different combinations can there be? How would you pick those 5 CDs? In that same way, we're talking about if you have 6 local bands that have volunteered, to perform at a concert, then basically we want to know in what order will those bands perform, because obviously whichever one is going to be your headlining band, you wouldn't want them to perform at the beginning, because if they perform at the beginning, nobody's going to stay for the smaller bands. So you obviously, that order is going to be crucial when you're putting these lineups together. So this is kind of where the idea of what are all the different possibilities that we can come up with when we are looking at these. So we are talking about 3 shortcut counting methods. And, of course, those are going to be your fundamental principle of counting. And then we also have combinations and permutations, which are, again, different types of calculations we do for counting. So basically, with your first example, with the 2 pairs of jeans, 3 shirts, and 2 pairs of shoes, you can actually create 12 different outfits from that. Choosing 5 CDs from a group of 50, you actually have 2,118,760 different combinations of how you could choose those 5 CDs. And then with your 6 local bands who are going to be performing at a benefit concert, there's 720 different lineups on how you could arrange those bands to play. So all of these are basically what we're talking about in terms of how do we do that counting, how do we come up with these different possibilities. And this is what we call as combinatorics. So that's basically the study that we are looking at over here. So let's start out with that first one, the fundamental principle of counting. They're talking about, even if you think about all the different decisions we make in the day, they're talking about ordering from a menu item. What clothes are you going to choose to wear today? What are you going to do when you're, trying to buy a new car, kind of thing. So, they're talking about, if you just think about if you're at a restaurant and they're asking you, do you want soup or salad? If you choose salad, then they will ask you, okay, what type of dressing do you want? What kind of side vegetable you want to go with your food item? What's your entree, your beverage? What kind of dessert? So these kind of examples, because think about it, for each category, there will be choices, right? You may have 2 or 3 different types of soups. There can be 2 or 3 different types of salad options. Of course, dressing, there's always an increasing amount of dressing out there. You never know which one you're going to go for. So when you are actually looking at this fundamental principle of counting, it's for more of these examples, like the outfit example we had at the beginning, or, think about ordering food, kind of thing. So we are talking about, you can actually come up with these different possibilities by using this idea of a tree diagram. So basically you look at, all the different choices you have and how many ways is it going to break down into. So basically they're talking about how a tree diagram can consist of clusters of line segments or branches, and you can see, this is going to be your starting root, the first decision you are going to make, and then it's going to branch out into two more decisions depending on how many choices you have. And then, how many choices the second decision had, it's going to break down, further down the line as you go forward. So they're talking about, well, in this case, they're actually just talking about if you had to make two decisions, you have two choices for decision one and three choices for decision two. So you can see decision one gets broken down into those two choices. If you went with choice one, then from decision two, you have to choose from three different options. If you went with choice two on that first decision, then again, your second decision, you still have to make three different choices. So you can see two choices from the first decision, three choices from the second decision. You would actually have six different possible combinations possibilities that we could come up with. So basically, let's take a look at this example that we just talked about with the two pairs of jeans, three shirts, and two pairs of shoes. How many new outfits we can come up with? So with our starting point, we're choosing between, are we going to wear jeans one or jeans two today? So those would be our two branches from the starting point. Now, depending on, did you choose jeans one, then are you going to choose the first shirt, the second shirt, or the third shirt? Or if we chose jeans two, then again, which shirt are we going to go with? Once you have selected your jeans and your shirt, now it comes down to shoes. So then again, if you chose jeans one, shirt one, now which shoes are you going to go with? Or jeans one with shirt two, again, what are the shoes? Same thing. So you can see how this breaks down into, all of these different options. And then depending on which one you went with, this is going to be our final choice, which is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And that's exactly what they told us. We would have 12 new outfits from, this little shopping spree that we had. So we had 12 different outfits. And, a tree diagram really kind of helps you visualize, but it also helps you see, what all those different combinations can be. But, obviously, if you had a lot of bigger numbers or multiple different options to choose from, that tree diagram can get pretty tedious to come up with, and it can get pretty complicated to try and keep all of that track of. So basically, the way the fundamental principle of counting goes, you take each of the options that each category has. So we had two jeans, three shirts, and two shoes. You multiply them together, and that tells you how many different possibilities you have. So that's the idea behind this fundamental principle of counting over here. So they're talking about, you take the total number of possible outcomes of a series of decisions, and you're basically finding that by multiplying the number of choices for each decision or for each category. Now, this one here, they're talking about, draw a box for each decision. Then you're going to enter how many choices you had for each decision and then multiply at the end. But, obviously you don't have to do the box part if you don't want to, because I honestly don't. So let's see how we can use this fundamental principle of counting over here. So we are coming up with a serial number that consists of two consonants and then followed by three non-zero digits. So remember, when we're talking about consonants, that means they are not going to have, your vowels, A, I, E, O, U in those. So three digits, and then after the three digits, you are going to have a vowel. So if you think about this, they're asking us to come up with, determine how many serial numbers are possible given the following condition. The letters and the digits cannot be repeated in the same serial number. Okay, so letters and digits cannot be repeated in the same serial number. So let's take a look at this guy over here. Again, like I said, if you don't want to draw the boxes, you don't have to. So if you are not using vowels in that first one, they are only asking you for consonants. There are 5 vowels. So that means you will have 21 different letters left behind once you remove those. So your first box will have 21 different letters to choose from. Now they are telling us our letters and our digits cannot be repeated. So you can see for the second box for the consonants, we're only using 20 letters instead of 21, because the idea is whatever letter you have already used for that first place, you're not going to be repeating. So you are going to subtract one number down and you will only have 20 consonants to choose from. Now they are also telling us we should have 3 non-zero digits. So that means you're only going from 1, 2, 3, 4, 5, 6, 7, 8, and 9. So we are only looking at 9 digits. Now whatever number we ended up using in the first place cannot be repeated in the second one. So out of the 9 digits, you have used one, which means we only have 8 digits left behind. In the 8 digits, you have already used the second number, so that means you will only have 7 to choose from in that last spot. So again, each of these number goes down by 1 as you make your selection. And then for the last place, they said that should be a vowel. So of course you only have 5 options in that case. So that would be your 5. So you can see you take how many choices you have for each of these places in our serial number, and then you can come up with how many different possibilities you have. So without repetition, you will end up with 1,058,400 different possibilities. Now with the second option, they are saying letters and digits can be repeated. So it can look something like this number over here. And the first one where no repetition is allowed, it would look something like this. So with repetition being allowed, you're still following the same format, but now our numbers do not decrease by 1. So you can have 21 consonants for the first place, 21 consonants for the second place. You can have all 9 digits for all 3 of these places, and then we still have 5 vowels. And you will see when repetition is allowed, you have a larger number of possibilities, because now you have 1,607,445 different options. So without repetition and with repetition, it makes a difference. And this is the kind of idea, we use for our license plates also, because, especially in Colorado, we use both letters and numbers on our license plate. So, and they have to keep changing their I don't know what to call it, whatever rule they are using to create these license plates, because the more and more people are buying vehicles or moving to Colorado, they are needing more and more license plate numbers. So, they're always trying to come up with which will give us more possibilities, more options, so that, we can have enough license plates to generate, as people are requesting new registrations. So that's basically the idea behind the fundamental counting principle. So let's take a look at an example over here. And how about, let's take a look at number 4 over here. This is 2.2. Let's open up 2.3. All right, so we are looking at number 4 from 2.3. And this is talking about Sammy's sandwich shop offers a soup, sandwich, and beverage combination at a special price. They have 3 different sandwiches to choose from, turkey, tuna, and tofu. They have 2 different types of soups, minestrone and split pea, and 3 different types of beverages, coffee, milk, and mineral water. So for part A, they want us to use the fundamental principle of counting to determine how many different meal combinations are there. And then part B, they are asking us to construct a tree diagram so that we can see, what all those different combinations would end up looking like. So let's start with the fundamental principle of counting. What do you think? How many different possibilities do we have for this combo with the soup, sandwich, and beverages? So using your fundamental principle for counting, what would you come up with? Again, basically what we just talked about in these examples, or what we looked at over here with this jeans, shirt, and shoes example. You can use any one of them to guide you. And they didn't mention anything about repetition or anything like that, so you don't have to worry about any of those. All right, yeah, very nice, Markley. That's exactly what we have is 3 times 2 times 3, which will end up giving us 18 as the answer. So for this guy, 3 times 2 times 3, so you will have 18 possibilities. Oh, I can't spell. Alrighty, now for the tree diagram part, let's try and do that over here. Alrighty, so let's take a look at how we can do our tree diagram here. So, we are going to have our starting point for the tree diagram. And actually, if we're starting out with sandwiches, we're going to need 3 branches. Okay, so you would start with your, turkey, what was it, tuna and tofu. And these would be for our sandwiches. And then since we are going from 3 sandwiches to 2 soups, then you would have to break each of these down into 2 further categories for the soups. And then you would have to go ahead and list your soup. So I would like you guys to work on that and let me see what you can come up with. Okay, so hopefully you should get that request again through your chat for the whiteboards. Basically, we've got our turkey, tuna, and tofu. Those would for the sandwiches. Then our next category would be for the soups. And I think we had minestrone and split pea, I think. So you can just abbreviate that if you want, minestrone and split pea. And then I think your next category was 3 beverages, which was coffee, milk, and mineral water. Now remember, from each branch, you should have those multiple options coming from. So if it helps, you can look at the tree diagram for those outfit example we have looked at with the 2 jeans, 3 shirts, and 2 shoes. Alrighty, let me see. Just make sure you're giving yourself enough room, and you can abbreviate for your drink beverage choices. C for coffee, M for milk, and I think they had mineral water, so W for water. So that way you're not, using up too much space with writing the whole words out. And then remember, at the end, you have to list all your possibilities like we did with these possible outfit examples like you had, the list of possibilities at the end. So, yeah, Kiara, you seem to be on the right track over here. Markley. Okay, so Markley, go ahead and start listing what those 18 different options would be, because it looks like you're actually done with your tree diagram, so that looks good. Logan, looks like you're working through yours. That's nice. Okay. Lorena, you're kind of there also. Alrighty. Maribel, looks good. Isabel, that looks good. Macy, that looks good. Burgundy, nice. Oh, looks like you're still working through that. Cooper. Cooper, looks like you missed something in there, because I'm seeing the sandwiches. I'm seeing part of the beverages, not all of them, and I'm not seeing the soups at all. So it looks like you missed your soups and you don't have all your beverages in there. And Ethan, is that you with the E on your board? Yeah, okay. Yeah, Cooper forgot your soups. Ethan, that is also looking good. And I know some of these are, I don't know if you're using your finger to do this or your mouse, but I know it's kind of hard to draw all of these out. So once you have your possibilities listed, let me take a look. So Aaron, the beverages are coffee, milk, and mineral water. So you can do, if you don't have enough space, you can do C for coffee, M for milk, and W for water. Alrighty, let's take a look. Becca, looks like you're still working through yours. Okay. Markley. So are you using V as the symbol for your minestrone soup, Markley? Yeah, okay. And so you should have turkey, minestrone, coffee, and then water milk, split tea, coffee, water milk, and then tuna, with minestrone, coffee, water milk, and split tea. Okay, very nice. That looks good. Burgundy. You've got minestrone, turkey, and then coffee, water milk. Turkey with the split pea, coffee, water milk, tuna. Okay, so you've got a couple more options you got to put in there. Very nice. Maribel, I can see you have started typing in your answers already. Yeah, so remember, since we did the first part and we know we are going to have 18 different combinations, when you are finally done with your tree diagram, make sure you are looking at 18 different options. So right now, we've got, you know, obviously 3 times 2, which will be 6 different options. And then when we bring in our beverage choices for each one of these, that's when it's going to triple. With our coffee, milk, and water. And then these would be our beverage choices. So let me see if I can make this bigger for you. So you, hopefully if you can see my screen, then you can see this is kind of what I was talking about, the whole list of what those 18 different possibilities will be. So this was Burgundy. Here is Markley's board, what it looks like. Maribel, looks like you were able to get your different choices in there. And then I can see Macy and Lorena. You guys are typing your answers in there. So basically, you know, that's kind of the idea behind this fundamental counting principle or fundamental principle of counting is you can use the tree diagram, but like I said, sometimes those tree diagrams can definitely get very tedious and long because depending on how many choices you have. Or you can just use the idea of take how many choices you have for each decision or each category and then multiply them together. And then this example over here is highlighting sometimes we may say it's okay for repetitions to occur, and sometimes it's not okay for the repetitions to occur. So then you can kind of see the contrast between, how our number of possibilities will change depending on how many um, repetitions are allowed or not. So something to kind of keep in mind as we are working through these different counting rules. So next time we will talk about factorials and the permutation and combination. So again, guys, your homework is already online. Make sure you are working on your homework. I will go ahead and open up the quiz for chapter 2, and then we are also going to be doing chapter 3 before we take a combined test for chapters 2 and 3. So, probably next week we will try and finish chapter 2 and 3 and then get ready for our exam after that. So if you have any questions, please let me know. And you can stay back. And if not, then I will see you guys on Tuesday morning. So have a wonderful weekend. Take care, guys. Be safe.
Um, you said that the homework for chapter 2, all of it is